Hello, in this screencast we're going to go through an example of applying the NeoPrism analysis suite to a recording. We're going to look at using coherence analysis to localize a seizure. This is Michael Guest, VP of Research and Clinical Applications for Persist, and this PDF is really a very nice step-by-step guide in using these tools, but also does a lot of explanation. Now, these tools were originally developed some decades ago by Drs. Langerland and Charborough, and those were written to run on the VAX system back in the day. And what we did was, using the application notes that were developed for that system, we went ahead and developed entirely new within Persist at that time these tools to run within Windows. So they're based on the tools that were developed by Langerland and Charborough and recreated to run in Windows. Now, these tools do use some earlier Windows conventions. Nevertheless, this is Persist 15 we're going to be running this within. And Insight 2 is a user interface for Persist. So when you launch Persist, we're going to look at that. That is the current generation of user interface. We'll go to a Tools menu in Persist and launch Insight 2. That one has more buttons. It is a more traditional EEG review interface, and it also includes these NeoPrism tools. Now, what do we have in this PDF, and why am I starting with this? This one gives a nice description of the sample recordings, which can be made available, and starts out talking about the basics of digital EEG, and talk about using filters, whether they're infinite impulse response, IIR, or finite impulse response, FIR, and some of the differences between those, and gets right toward looking at autocorrelation, using cross-correlation analysis, and these are all clinical examples based on those three recordings. Of course, you can apply them to your own. The one that we're going to look at is this, using coherence analysis to help localize a seizure. And the reason we're going to use that is because it'll cover a number of actions to do within the software. We're going to be marking ranges. We're going to be placing vertical adornments, which are the analysis tools which appear vertically within Insight 2. And we're going to be modifying the properties of that to perform this analysis. Now, once you know how to do those operations, every one of these other processes, it basically follows the same convention. So we're going to use this as a nice example to do that. So let's go ahead and go a little bit further into this. As soon as you start going to it, you see the information about each one of the sample recordings, the patient's history, imaging for each one of the three files. I know I'm going quickly through this, but again, you can read, you can have the PDF, you can get the PDF and go through this, and it makes for a very helpful study. Right off the base, we start talking about the filters. I had mentioned that, and some of the technical aspects of it. And then it talks about the different applications, so autocorrelation, cross-correlation, time delay estimation, and I'll go ahead and stop that. Defining and applying a custom filter. You can do that from Insight 2 today. You can also do it within the Persist interface, and I'll show a little bit of that. But let's go ahead and jump to that part of the guide. And look at this. So it begins talking about what coherence is and some of the other measures associated with that. So we're going to look at coherence, 0 to 1. We're going to look at phase relationships, either minus 180 degrees or positive 180 degrees, which talks about the phase angle while we're looking at signals in different channels, whether it leads or lags, and also looking at phase-dependent spectrum. These are all described in here. That last part really talks towards doing the other type of coherence analysis that we'll do when we're wrapping up. Okay, so let's follow the steps here. We're going to do it a little differently because we have the trends in Persist that helps us get to the point of interest. In this guide, it wants us to go to this point in this recording. So let's go ahead and bring up that recording in Persist. And we have a couple of seizure detections here, and we can see from the rhythmicity spectrogram, we have an evolving rhythmic pattern. And the amplitude of the EEG, the background EEG, is not very high. So what we can do is click on this scale here. Rainbow part, we can move this down to make that pattern a bit darker. So just as you would adjust the gain for reviewing EEG waveforms, you can adjust the gain of spectrograms. Same thing for the FFT spectrograms. So, as a matter of course, sometimes you get recordings with higher or lower amplitudes. And this is how you adjust for that using the rhythmicity spectrogram controls and the FFT spectrogram controls. Let's stay at the task at hand, though, as we want to get to the onset of the seizure. So I'm going to click here, and we see that our time is right around where we want it to end up. So let's go to Tools and select Insight 2. And I'm going to bring this back down into the portion of the screen that I'm sharing. And this is Insight 2. And we can see that, different from the previous interface, is we have all the tools up at the top, the buttons, to change various aspects of the display and so forth. Whereas in the Persist program, a fair number of these are actually under Preferences, General Preferences, just to tidy up the interface a bit. So, same program, different UI. And importantly, this is where we have this right-click menu. So I just press the right mouse button, and we get a whole menu of options. And what we're going to be exploring is frequency domain analysis in just a moment. First thing, though, let's have a look at how they're viewing the EEG. So I'm going to bring that PDF back up. And we can see here that this is using a montage that's showing all of the channels. We have a subtemporal chain that's applied and one additional electrode on either side. So slightly enhanced subtemporal chain application and an average 31 reference. So how do we get together? Well, there's 31 scalp channels here, so that average would be the average of all these. And notice they have all the filters turned off when performing this. Filters, IIR filters can time shift faster frequencies a bit, or phase shift them rather. Analog filters would do the same thing. So FIR filters, which are a little more computationally intensive, can do that to a much lesser extent. But since we're going to be looking at millisecond time differences, we'll just turn the filters off for this particular analysis. So that's, well, it's a fairly important thing to keep in mind. We're going to leave filters off when performing this sort of time delay measurement. Let's go ahead and look at our average reference. Bring Insight 2 back up. Now I've already created that montage, so I happen to call it subtemp average 31. And there it is. So let me move this out a little bit so we're not clipping any channel labels. By the way, that's something that's new in Persist 15. I believe it's with version B and later. Previous ones you couldn't really change the size of this. You could change the font size though. This is particularly helpful when reviewing intracranial recordings. But how did I create this montage? Well, right click and then create montage. Now this does not show all the 1010 positions. So to show those, we can go to 1010 and then you can begin selecting electrodes. So we go F9, T9, TP11. That's not showing up here. So let's switch to all. And then we can see where TP11 is. Right there. Add TP11. Then we can go back to our 1010. And then we'll select P9. And then we'll insert a separator. And then we'll do F7, T7, P7. Notice I'm leaving the reference of these all set to CZ, because I still have to build my average reference. So I'm just going to let it assign a CZ reference for now, and then create the average reference. Rather than going through all the button clicking for this, I want to cancel this because I've already done that. Let me discard my changes. So initially I started with all of these channels to CZ. Then right click, edit average reference. And this is the average 17, this is the average 12. Now these are important because these are hard-coded references in Persist. So you can't modify these, but you can save them or change them and give them a new name. In this case, though, I didn't have to go quite that far. But this is, these are hard-coded. This is the reference actually that's used by the spike detection. And this average 31 is a reference that I created by doing select all. And EK1, well, that's EKG channel. I don't want to have that included. And so these are the only ones that are going to be selected for that reference. It happens to be 31 of them. And I can normalize and equalize. That's important. You want all the weights to add up to 1. Of course, in Laplacian references, there's a reference for each channel. They use the surrounding ones. Some might have 3, some might have 4, depending on your particular design. The persist Laplacian montage will use 3 electrodes when you get towards the edge of the electrode array. But the main thing is that they should add up to 1, whether it has 4 surrounding it, 3 surrounding it, or in this case 31 electrodes all averaged together. And that's what normalize does, makes them add up to 1. Equalize, of course, sets them all to the same value. And I've already created that reference, so I don't need to do that, but that's the first step when you're looking at these is, as it explains in the PDF, is you can use a bipolar, you can use any montage really for this sort of analysis, but like in anything to do with waveforms, a review, you'll find that using bipolar montages, as it describes here, and referential montages with a common reference is generally greater than in bipolar montages. So it talks about the effect of coherence measurements on that, but you can use any one that you like. But in this case, we're going to use the average 31, and we're going to mark a range. So let's go ahead and do that. And the place in the recording that it was going to go to, let's double check that position in the guide. It's at the onset, so 13:53:51. And we are right there. 51. There's where persist mark the onset of the seizure. Now let's go ahead and change our gain. And again, the gain that you select is a visual thing. It won't affect the measurements. And we want to turn off our waveform filters. That includes the notch. So our low, high, and notch filters are off, including artifact reduction is off. And in Insight 2, in that interface, this is where you can toggle that under the artifact reduction option. That's step 1. Next step will be to mark a range. And so what we'll do is we'll right-click on the EEG. Let me click a little higher so that's not off the screen. We'll do Insert Range. And in the example, they selected 3 seconds. I'm at 3.01. By the way, if you need to adjust these, you can grab and hold the black caret that's at the top of the cursor. This doesn't matter. It's not important that we're precisely at 3 seconds for this particular example. And notably, this gray bar between this, we can move this around. We can change its position. Well, we'll have it start here. Next step is we're going to insert a vertical adornment, and we're going to pick frequency domain analysis. Now we end up with FFT spectra for each one of the channels, and it's out to 32 Hertz to make it a bit easier to see the areas of interest. In this case, we're looking at lower frequencies, given the nature of the seizure activity. So I'm going to shorten this up a bit as we get going. I'm going to change that frequency range. Let's refer back to that PDF. And that's what it says to do. Notice it says Insert Vertical Adornment. So as you follow this step by step, T10 will be the channel that we're going to compare. So each channel output is going to be compared to T1, or T10 rather, and the reason for that is that's the one that appears to have the highest amplitude going into this particular seizure. So we want to see which channels show the highest level of correlation, what the phase relationships are, which is lead and lag, and also look at the, we're going to look at coherence, or the correlation, and we're going to do phase relationships and the frequency measurements. So anyway, and we're going to select which ranges to analyze. You can analyze multiple ranges. We're going to look at that Y scale option and why we do that. And we're going to end up with a display that looks like this. Let's go ahead and go back to Insight 2. So to do that, this is where this right-click menu is going to come in handy. And note that something that may not be obvious is between the waveform display and the FFT, or whatever the graphs are that you're displaying. When I put the mouse between them, it becomes a 2-headed arrow, and that's for resizing. So if I click and drag, I can resize that. If I click and hold on the EEG, it becomes a hand symbol, and I can move the EEG over as well. Notice that range stays where I put it. All right. Right-click Properties. I'm going to pick Coherence Separated. We'll look at Coherence Combined in a moment. Data ranges will be not the full EEG page. I'm going to use the ranges that I've set, and I'm going to say Selected because I've selected that range. It makes it more explicit. And then Spectrum 32 Hertz. 0 to 32 Hertz is the default. You can, of course, go to half the sampling rate in this, but again, we're looking at this primarily in lower frequency ranges, so I'm just going to cut that roughly in half. And that's just going to make these displays a little bit larger. So why are these flat on both sides of this? And this middle one, which is showing the phase relationships by frequency from 0 to 15 Hertz, that's that last step. When you go to shared axes, we have to deselect the common scale. And why is that? Well, the first one is showing the amplitude by for FFT in microvolts. The next one is showing plus or minus 180 degrees. The last one is showing coherence 0 to 1. Those are all different scales. With that check mark, remove the shared y-axis, then they can all auto-scale. And here are a couple of frequency peaks in this, here and here. Let's just visually assess this, and then we're going to apply a cursor to look at some numeric outputs from that. So at this frequency, this is roughly 2.5 Hertz. Then I can look here at roughly 2.5 Hertz and see what the relationship is. And that's something else I need to do. I didn't change the cross-correlation channel. Visually, you can see, oh, wait a minute, these are flat. Why? Because it's undefined for the phase, well, it's 0 for the phase relationship. No leader lag, and the coherence is undefined. So let's go ahead and go back to Properties and pick that channel. Move this box up a little higher so you can see that. The cross-correlation channel is super important. T10, that's the channel that appears to have the highest amplitude. Click OK. And now we can see this is the channel that I'm making the comparison with. Super important. So now we've got this peak here, and as we look about 2.5 Hertz here, we can see again phase relationship. Of course, it's in phase with itself. And if we look across at some other channels, for instance, F10 and F8, we can see that very little in the way of phase difference at those frequencies. And if we look at the correlation, we can see those are very high. So T10 compared with T8 and F8, the correlation is nearly 1. And we can see that in other channels as well, where it's highly correlated. But the other thing to keep in mind is the phase relationship. As this goes below the line, those minus ones, it's leading, and above, it's lagging. So that's the phase relationship. This is at the bottom of this curve. It's minus 180, plus 180. So that's the phase angle. So how do we measure this? Right-click. And I'm going to click up here so you can see the whole thing. Insert cursor. It's around 2.34 Hertz, and I believe the guide said to do it at 2.5. Really, I just picked the peak of interest. Let's say you wanted to set that precisely. For whatever reason, you can right-click on the black caret at the top, select Edit, and then you can type in a value. Now we've set that. Let's right-click on one of these graphs here and do Insert Vertical Adornment and FDA Table. Click a little bit to the left here so it's not clipped. Now I've got amplitude, phase, and coherence. And as we visually estimated over here, we can see the coherence is high. Anything above 0.7 is fairly coherent. So we can have some high values of coherence, but here we can see 167 degrees, 0.6 degrees out of phase, minus 176. If we look here, though, we see this leads slightly, negative 5.9, and that's the amplitude at that frequency. So amplitude, phase, coherence. Let's add another one. You see these are getting a little compressed. Have a little space over here, keeping in mind that you can size the right or the left boundary of these just by putting the cursor between the two displays. It becomes a two-headed arrow. Just drag them and resize as you like. So let's place that second one. I'm going to insert a cursor here, and 3.91 I believe they use 5 in the example, but let's go ahead and just type that in there like that and refer back to this and see what frequency they use for that second one. As I skip through the guide at high speed, 2.45 and 5 hertz, and then they have the table of values here. So let's go back to Insight 2. I can select the cursor I want to make the adjustment to, edit. It's already 2.5 and 5 hertz. Okay, so let's move this boundary over a little bit here so we can see more of the numbers. And again, we're looking at amplitude, phase, and coherence. This is for the 2.5. That's what's printed up at the top, and the 5 over here. Now, for whatever reason those numbers get clipped off in your display, you can click View and Display Options, or you can pick it from the menu. But there's the display options there. And then if you go to EEG page size, this is a top margin and a bottom margin. If I do the top margin, you can see it just bumps it down a little bit. This really depends on your display resolution and font scaling or zoom level, depending on your flavor of windows. But if you need to add a little space top or bottom for any of these legends, that's how you do that. Okay, that covers this part of it for going through the user interface. Let's look at the other example because we're going to take a couple of other options there. And by the way, this guide goes through making interpretations based on what they found. But the next piece, let me scroll back up. Pardon the scrolling. Is we're going to look at coherence combined. Yeah. So this example continues on talking about using this coherence combined. Other parts of this guide you can go through: phase encoded Fourier spectrum analysis, and there are a bunch of other tools. You can even do independent and principal component analysis, wavelet analysis. There's a lot of stuff. I'll show just a couple of those briefly at the end of that without getting into any depth at all. Let's clear this out. We'll go right-click, delete, and that removes that. We don't have to delete this. We can just modify it because this is, again, a variation on this theme. So we'll go to Properties, right-click, and go to Properties. I want to do Coherence Combined. And I'm going to superimpose these because, as you noticed in the guide, for the multi-part options, if this is not selected, I'm going to see 3 separate parts. But for this, I'm going to superimpose them. And shared axes, I do want to share the axes for this. And the reason is because if we go back to the guide, it explains a set of combined spectra. So the spectra show 3 superimposed curves. So conventional amplitude spectrum, that's the FFT, always positive, of course. Well, except for the imaginary stuff, but again, we're showing the FFT. Second is amplitude coherence spectrum. And then phase dependent or amplitude coherence spectrum, positive or negative. And so from that, it describes what you're seeing in those graphs. And that's why it's handy to have the same recordings that were used, so you can look at those and see, all right, this is what I'm looking at. Let's go ahead and drop a cursor in and show the same table. But again, this goes through the review of what they're looking at. And I think that's kind of a nice piece that they've added to that document. Let's go ahead and bring up the program. We'll drop a cursor in here. Insert cursor. Insert vertical adornment, FDA table, amplitude, phase, coherence, lead or lag, and then the phase dependent spectra. So those are all put out in numeric form. And the PDF goes over those. Again, this is mainly going through how to navigate the user interface because these are more traditional Windows conventions as far as having the mouse pointer change when you're at a certain point of the screen. With mobile devices having taken over pretty much all areas of influencing user interface development, some of these things may not be as obvious today as they were back then. So this is just something that helps streamline the process of learning this, is how are these screen elements navigated. Okay, let's look at some other things with respect to this. I'm going to go ahead and delete this. Some of the other things that you have for insert vertical adornment, you have wavelet transforms, continuous and discrete. That's interesting looking. Let's do the discrete wavelet transform. And here's the dialog for that. I went through that a little quickly. So I right click, do insert vertical adornment, and then I picked discrete component or discrete wavelet transform. If I go to properties here, by right clicking it, the DWT, this is where you can change all the parameters for this, the type of wavelet, lots of choices, shared axes, how you're going to display this, what section of EEG you're going to be looking at, the color palette, all those. So let's go ahead and delete that. So again, quite a few things here. Principal component analysis is displayed in the guide. Typically, that's more for separating artifact. But artifact sources tend to move around if it's muscle or eye movement. They're not stationary, or not as stationary as we might think. So that's where the automatic artifact reduction becomes quite a bit more useful. But you can use PCA to help localize a seizure as well. The other thing that we can do is insert an underlay. And these are interesting from the aspect of being able to visualize what it's doing in the context of the EEG. So that's just laying a continuous wavelet transform spectra over the waveforms themselves. And you can see during different excursions of the waveform what that looks like. So as a way of getting the hang of what these are actually rendering visually, that can be handy. And then you have matching pursuit. And of course, you can lay FFT spectrograms in there as well. So quite a few things under the right-click menu to explore. So just one thing is, of course, montage and reference matter. When you're doing coherence measurements and looking at time delay estimations, go ahead and turn the filters off. That eliminates the opportunity for any phase shifting of faster frequencies and that. Generally, it's not a concern, but when you're talking milliseconds, it's a good idea to do that. And other than that, definitely go by the guide or go use the guide that we provide and the recordings, because this is meticulous in going through each one of the steps and then talking about the output of these in the context of the recording. So I think it's a really valuable resource in learning how to do these things. Any questions, feel free to let us know. Always happy to meet by web conference.